Okay, so I think I'll be continuing to the second lecture. And as I mentioned earlier, this is the next two lectures. And what is the topic of the rest of the day? It's just basic OpenMP stuff. And there is nothing task related here. I just included this content and based on the information I got from the registration forms, where I asked people to indicate what is their level of experience, level of experience related to various topics, including OpenMP in general. And there we had several people who were not that familiar with OpenMP. So I decided to include these two short lectures here to basically teach people the very basics of OpenMP that is required for tomorrow morning's OpenMP tasks lectures. And there's also a couple of hands-ons included here. And my plan is to go through these materials reasonably quickly, have a short break there so people can do the hands-ons from the first lecture, and then do the second lecture after that. And then I'll be staying here for a while until I eat my lunch to see if there are people who have some OpenMP specific questions. If you're already familiar how OpenMP works, then I don't take any offense if you decide to go and leave and join us tomorrow morning when I actually start discussing OpenMP tasks. For everyone else, this is going to be a brief introduction to OpenMP-based parallelism. So just to start, the first lecture, this has two primary learning goals. The first one is to learn to use a parallel construct in OpenMP. And this is something you need when you're doing task-based programming in OpenMP. Everything has to happen inside the parallel construct. And then we also learn a little bit about data sharing rules. And this is a second very key thing. Data sharing rules specify how the data is shared among different threads. And it also then later on defines how the data is shared between tasks. And this is a key thing to understand, because otherwise you might get the results that are very confusing. And if you don't understand the OpenMP data sharing rules, at least on a basic level, there is no way for you to understand what went wrong. So OpenMP stands for Open Multi-Core Processing, is a programming API for shared memory parallel programming. So there is no distant memory support. It's all happening in a shared memory. Of course, these days you can also use OpenMP to do GPUs, and that runs in a separate memory space. So there's some distant memory component there, but it cannot communicate across multiple nodes. It's all happens in a single node that may have a GPUs in it. And it supports C and C++ and also Fortran. And it is based on a pragmas or directives. So you take your code that doesn't run in parallel, and then you can augment this code with this additional information that tells compiler how the compiler should go and parallelize the software. As I already mentioned, these hands-ons that happen today, they are very tiny, so you should probably run them on your own computer on a Kubernetes login node. And there's one key thing you must understand about login nodes, which is that they are not meant for long-term computations. And therefore, they have various safeguards that try to make it less likely that someone would accidentally run a huge computations on them. And one safeguard there is that there is an environmental variable called OpenMP num threads that tells OpenMP program how many cores it can use. And by default, this is set to 1 to make it show that people don't accidentally run OpenMP programs using all the cores on the login node. But in this course, you may want to run this command once for each session that you have open. And this pretty much just tells that the OpenMP num threads is set to 8, meaning that your program is allowed to use up to 8 CPU cores from the login node. And if you don't have it set like this, then your code will actually run sequentially. Even though you have a parallelism enabled, it's just telling the OpenMP runtime system that it can use this 1 core. So this is something you have to do for each session that you're running login node. This doesn't happen on the compute nodes. There, this information is communicated when you're specifying how many cores you want. It's only the login node. So let's go back to the actual materials, and I would like to look at this very simple hello world program that you compiled earlier this morning. And we can compile it, and it will just print us the hello world line. There is nothing special there. So let's go and add an OpenMP pragma there. And it is this parallel construct I talked earlier. So we will just augment the source code with this pragma, and then we will compile it. Noting that this time we have to give this additional argument for the compiler, telling it that there is going to be OpenMP pragmas in the source code. And what happens this time, you will see that this hello world line gets printed several times. And it happens several times because it is actually running this line of code in parallel multiple times. And the number of times it can be executed is the number of CPU cores the OpenMP implementation C, or in case of the login node, it is the number specified here with the OpenMP num threads. So if you set to 8, then you will see that this hello world line will get printed 8 times. And here is the first challenge you can do afterwards, and there is always a solution that is hidden by default. But if you want to see the solution to it, you can go and click this plus sign here to see how it's supposed to be solved. So that was the hello world program. So what was exactly this OpenMP pragmas and the construct we have? So in C and C++, each pragma looks like this. So you start with the keyword pragma, and then comes OMP, standing for OpenMP, and then you have the directive name, and then you have a set of clauses, and then you have a new line. So that is new line means just enter. So you start a new line of code. And you can divide these, if it comes very long, you can divide it multiple lines. Then you have just as a backslash, immediately followed by a new line. So if you have anything after this backslash, it won't compile. You must have a new backslash and a new line directly after it. And in this way, you can divide very long pragmas to multiple rows. And earlier you already saw this parallel construct. So here this keyword here is pragma OMP parallel, and then it's followed by a set of clauses, a new line, and then there is a structured block of code that follows it. And what happens here is that when the OpenMP encounters this structured block here, it will create a team of OpenMP threads that execute the parallel region of a code that is constructed from the structured block that follows this pragma here. So the structured block that comes after parallel pragma is executed in parallel by a team of threads. In the early example, the structured block was just one printf function call, but you can use these curly brackets here to actually make it so the structured block consists from several statements. And this is usually what happens. If there is no usually point to run a single printf line in parallel, what you have much more complicated structured block that is being executed here. And all the threads in this team execute this structured block. So if you have 8 threads, it will get executed 8 times independently of each other. Then we had these clauses that come after this pragma OMP parallel. We have a set of clauses here, and this changed the behavior of this parallel region. And you can see that there are several of them, and I'm actually returning back to this later. But the 2 key ones here are the if clause. So you can give an if, and then you give some sort of statement that can be evaluated as true or false. And this can be used to enable or disable the parallel region. So you can, in dynamic manner, run things, same code, both parallel and sequentially. And then you can actually force the number of threads that is running there with the num threads argument. So you can tell it that this parallel region should be executed with 3 threads instead of 8, for example. And this is actually a topic of the second challenge hands-on that I've made for you here. Then I'm coming to the key topic that you should really understand today, which is data sharing rules. Because these parallel regions are executed in parallel by multiple threads that might go and access the same data concurrently. And we must somehow tell OpenMP how these kind of issues should be resolved. So if you go and, as an example, look at this slightly more complicated hello world program where we have just a number, integer value number 1, and then we will have a parallel region here running with multiple threads which runs a printf. I think the number is, and then it's going to print the value of the variable number, and after printing, it's going to increment it by 1, and that's it. And now you would imagine that what would happen here, and what you see is actually this. And the key thing to note here is that, of course, it will get printed multiple times, but it seems that the same number gets printed multiple times, which can be a bit surprising if you have never done parallel programming. how is it that this number 1 now gets printed twice? And here also the number 2 gets printed twice, and here as well. And what is happening here? And we actually have a very good explanation what happens. The fact that the first observation that the lines are printed in arbitrary order is simply comes from the parallelism, because we have a certain number of threads running the parallel region independently of each other. Then you can no longer know anything about the order in which operations happen. But importantly, this variable number is going to be read and written multiple times by different threads in an arbitrary order. And what is happening here with the number 1 is that 2 threads have more or less simultaneously read the value of the variable number in and see that it's 1. And then they are going to increment it. But they don't see the change the other thread has done because they have already read the data in. And this is to visualize it. So a parallel region where every thread that is executing the parallel region is accessing the same variable number concurrently. And then you can know the current ending about the order in which it is read and written. And either to solve this issue or at least understand how the variables behave, we must understand that OpenMP has 2 primary types of variables. There are variables that are private, meaning that each variable has its each thread has its own copy of the variable, and they can only access their local copy, and no other threads can influence the value of the variable at any point. And then there are variables that are shared between all threads. And what is happening here is that this variable number is shared along all the threads that are executing this parallel region, and therefore they can actually interfere with each other's output. 3 basic rules define what is private and default, or shared by default. The first one is that everything that is declared outside the parallel region is shared. And we can look at this example again. We note that this variable number is defined outside the parallel region, therefore it's shared, and all the threads therefore share the same variable when they're accessing it. The second rule is that all variables that are declared inside the parallel region are private. So if we had instead defined the variable number inside the parallel region, then the threads could not interfere with each other's output. And the third one is something that becomes more relevant in the second lecture, which is that the loop counters. So you have a for I goes from 0 to something. That loop counter is a private by default. And here's an example. We have a global variable here. It is outside the parallel region, therefore it's shared. We have this variable b that is outside the parallel region. It is also shared. But then we have a variable called c that is now inside the parallel region, and therefore it is going to be private for each thread. And then I again have a next challenge for you to go and play with the sharded and the private variables a little bit and see how it changes the behavior of the code. Of course, we can also do this explicitly. So we can actually tell OpenMP that certain variables should be shared or certain should be private. And looking at the previous example, we have this number here that used to be shared because it's outside the parallel region. We can use the private clause and give it to the parallel construct and tell that number variable defined here should actually be private. And now you can see that the behavior, what actually happens is that instead of printing numbers, it is just everyone is going to print, I think the number is 0, which is, again, there seems to be no interference, but it's still a bit weird result because the number started as 1. So why is it that suddenly all the threads think that the number is 0? So clearly something went a little bit wrong. And the thing that went wrong is that now in parallel region, every thread has their own number variable, but this number variable is not in any way connected to this variable that is declared outside the parallel region. So these threads here do not know that the number was set to 1 at the beginning. They just take whatever default value it has, and for probably safety reasons, OpenMP is just initializing all the variables to 0 by default. So this is, again, might sometimes be the desired situation, but in most cases, this is not what we want. And to solve this issue, we must tell OpenMP that these numbers are connected, number variables, private number variables are connected to this shared number variable. And the way what we usually want to do is that at the beginning, we want to copy the value from the number to the private number variables. And we can do this with a clause called first private. And it behaves very similarly to the private variable clause, but it tells OpenMP that it should actually go and copy before this the thread can execute this thing. It should copy the value from this number into the private one. And when we do this, we can see that it's now printing that, as we expected, I think the number is 1, because before the thread can start executing, it has copied the value from the shared number variable into the private one. Final thing for this lecture is something called explicit data sharing rules. And this is something that usually gets recommended when you're writing an OpenMP program, which is that you can use the default clause to specify what is the default, what is the default for each variable? Is it shared or private? And in this instance, we are saying that default none, meaning that we are telling OpenMP that for all variables that exist here, it is undefined if it's a private or a shared one. And if you try to now compile this software, you will actually get this bit cryptic looking error telling us that the number is not defined in an enclosed in parallel region. And this is because we have told OpenMP that we are overruling the default data sharing rules, and therefore OpenMP doesn't know if a number is a shared or private variable. We have told it that it cannot rely on these default rules. And in this case, we actually have to go and specify that the number should be first private. And this is a generally recommended thing to do, even though it might appear as if it just adds extra work. But it forces you to think what are the data sharing rules that should be applied in this situation. And if you put by default, always put default none, then if you get the compiling error, you really have to think every single variable and think, is this supposed to be shared or private or first private in this context? It is not required for OpenMP program, but most courses on OpenMP you can find it's recommended that you do it in this way, just to avoid any bugs that occur when you are actually thinking that some variable should be shared when it's actually private or something like that. And then comes the final challenge that I would like you to do. And I think I would now give people, let's say 11:40 to do these hands-ons. And then I will continue to the next lecture. And then after that, I will be here for a while to let people do the remaining hands-ons and help if there are any issues with them. Okay, so I think we'll now continue to the last lecture so that I'm done with these lectures before noon. But as I say that I will be staying here for a while to see if people encounter any issues with the hands-ons afterwards. So this is the second lecture, Introduction to OpenMP, part 2. And during this lecture, you're supposed to learn about a couple of additional constructs. First, we have sections and section constructs. We have a loop and a for constructs. We have single master constructs. We have jitter construct, and finally we have barrier construct. And this is not a complete. Again, this is not a complete guide to OpenMP. This is just meant to cover the very basics you need to understand what the codes that we'll be discussing tomorrow morning are doing. So in the first, let's discuss the sections construct. So earlier you saw that when you had parallel region, it is going to spawn a team of threads, and all those threads are going to execute the parallel region in parallel concurrently. And this of course can be used to introduce some level of parallelism into your code, but quite often you are not simply repeating the same operation multiple times. You have a set of operations that you can do in parallel, but these operations are going to be very different. And probably the easiest way to accomplish a situation where you actually have different operations happening in parallel are the sections and section construct. So what happens is that this must be inside the parallel region already, so you must have a team of threads running. So declare that this is going to be pragma OMP section. So you start a section region, indicating that you will have several sections inside it. And then for each operation you want to define that can run in parallel, you will do a pragma OMP section and the new line followed by structured block. And then you can have as many of these sections as you want. And the way it ends up behaving is that each one of these sections defined inside these sections region can run independently each other in parallel. There are several clauses you can give it that mainly relates to the data sharing rules as done before. And this is meant to, again, visualize how things work in practice. So you are inside the parallel region. So you have been spawned a team of threads here. And then you encounter this sections region inside which you will define several sections. And now for each section, there is going to be a thread assigned to it that is going to execute the structured block associated with the section. And these sections can now run in parallel and everything's executed only once. And just to show you an example, so you come in a parallel region and then you have one printf statement. And then you start a sections region that has 3 sections inside. And each section is going to print on a different line. And then we are going to end the section region, and then we are going to end the parallel region. And the output of this program is not at all that surprising. So you can see that the line everyone exclamation mark gets printed several times because that is only inside the parallel region, and therefore every thread that is in the team is going to execute this line. But these 3 sections defined here, they are going to be executed only once. So this only me gets executed here once, not everyone else gets executed only once, and just me gets executed only once. And one way to make this code like disorder is that with many pragmas, you can actually combine them. So you can actually do pragma OMP parallel, indicating that you are starting parallel region, followed by sections, indicating that this parallel region here will contain sections that are each one of them are executed only once. So in this example, you will see exactly what you would expect, that we have 3 sections, each one of them is going to be executed only once. But of course, now, even though they execute only once, the order can still be arbitrary. But we have now moved along the same code being executed multiple times. We can now execute a different task and we can execute them concurrently in an arbitrary order. And then I have created a single challenge for you here, so you can do some playing with the sections. The main reason I'm introducing these concept sections is that these kind of behave the same way as tasks behave. So you would imagine that each one of them would be a task. So I have 3 tasks, but they don't have any inputs or outputs. So they will simply all run independently of each other. So they are not full-blown tasks, but they behave very similarly. And that is the way I want to slowly start introducing the concept of task in OpenMP by first talking about the older concept called sections and called sections. Then the second way how you can actually introduce more complex parallelism are parallel loops construct. And these basically allow you to take, let's say, a for loop and execute the iterations of this loop in parallel, assuming that iterations of the loop are mutually independent of each other. So if there's any kind of dependency between the iterations, then you cannot use this thing. But if you simply have a certain number of iterations being performed and all of them are independent, then you can use this pragma OMP loop, pragma to execute in parallel. And again, an example, we must be inside a parallel region, and then we'll say we have a for loop here, which has 5 iterations, and clearly there are no dependencies between the loop iterations because each iteration will simply print the variable loop counter variable. So we can introduce this pragma OMP loop and it will parallelize it. And here you don't necessarily see any parallelism here, but you can see that the order in which the loop is get executed is arbitrary because we are actually running each iterations concurrently in parallel, and therefore we can no longer rely on the previously existing order in this loop. Instead, everything gets executed in arbitrary order. There are a couple of interesting clauses you can take. The first most interesting is probably the collapse clause. And what it does is that if you're a situation where you have multiple nested for loops, then you can use the collapse keyword to collapse multiple for loops in such a manner that the iterations from all those loops can actually run in parallel. And this is something that you will be actually practicing in this challenge I have given you here. So you can see that there are two loops, and I'm telling it that it would actually execute the outermost loop in parallel, and that is exactly what is happening. You can see that the first loop iterations, the loop iterations gets executed in arbitrary order, but in the innermost loop, it's always executed in the same order, because this loop, in innermost loop always runs sequentially, but it just runs multiple times in an arbitrary order. Then, of course, if you want to shorten your code, you can just write a pragma OMP parallel loop. So you can just very easily parallelize an individual loop in your code if you want to do so. Or you can use an older keyword called for. So you can do pragma OMP parallel for that is currently work with the older versions of OpenMP. And again, the effect is always the same. The loop iterations are executed in parallel in arbitrary order, as long as the loop iterations are independent of each other. Then there are sometimes situations where we are inside the parallel region and we would like to execute one code, one structured block with just one thread. And this is something you can accomplish with the single and master constructs. So inside the parallel region, you will say parallel OMP single, and then a structured block. And this causes a situation where the structured block gets executed only once by one of the threads in the team. So in this example, we have parallel region where we have 3 printf lines, and between the first and second printf line, we have a OMP parallel single telling that this printf only once should be executed only once by one of the threads in the team. And this is exactly what you will see. We have this in parallel printed multiple times, then we have only once printed once, and then we have more in parallel executed multiple times. But one key observation here is that this in parallel only once, they are all printed before any of the more in parallel are printed. And this is because in a parallel, in a single region, there is an implicit barrier in the end of it, meaning that all the threads in the team are going to wait until this barrier has been reached. So you can imagine that you are executing this in parallel and lines here, all the threads are executing them independently of each other in whatever order they happen to be running. And then you encounter the single region where we have this one printf statement. But then there's a barrier that forces every thread to wait until the last remaining thread in the team has reached the same barrier, and only then it's going to allow everyone else to continue along the execution until they might encounter a second barrier. And again, everyone is forced to wait until all the threads have reached this barrier, and then they're allowed to continue. If we want to disable this behavior, then we can use a no wait clause to tell that there should not be implicit barrier at the end of the single region. And in that case, all these lines here would be printed more or less in arbitrary order, except that the line only once is printed only once, but everything else gets printed as many times as there are threads in the team. And then in addition to single, we also have a master struct, that a master construct that behaves very similarly, except that it is only so-called master thread. So the thread number 0 in the current team that can execute it. And then there is no implicit barrier at the end of the master region. So two differences, it's just selectively just one of the threads can do it, and there is no barrier at the end. Then there are sometimes situations where multiple threads have to access the same data concurrently. And then we have to implement some sort of protections for it. And the most powerful way of doing it is called the critical construct. And what is needed there is parallel OMP critical, and then you can give it the name, and then you can give it a couple of hints that we are not discussing today. The only part is that you just know that it has to the name. And this guarantees that at any given time, only one thread in the team can be executed in the structured block. If some other threads in the structured block is attempting to do the same, they have to wait until the previous one has returned to operations. So you could use it if you're someplace in the code, you're incrementing variable X, you can declare that this is a critical region, and you are giving the name that we are protecting the X variable. And then later in the code, you might have a second one where you're updating the variable X, and you're also declaring it as a critical region. And because these two critical regions have the same name, it guarantees that only one thread can be executing one of these critical regions concurrently. And then I have a single challenge for you where you take the earlier example that ended up just printing the number 1 multiple times, end up printing the numbers in arbitrary order and some numbers multiple times. And I'm telling you that you should now use the critical region to protect this update operation. By itself, this is critical. It's much more powerful because it's quite complex way of protecting a variable. It involves a lot of additional overhead. There is a second type of way of protecting variable called atomic operations. And it's much faster to implement, but there is no need for that particular construct in this course. So therefore, I will be only briefly mention the critical construct, because just to let you know that there is a way to access a variable in a protected manner. And the final thing to discuss is the barrier construct, and it's just pragma OMP barrier. And this will introduce an explicit barrier in your code, where earlier you had the single construct that had the implicit barrier at the end of it. In this construct, you can do explicit barrier wherever you want. And the behavior is the same, whereas the barrier, all the threads in the team must encounter the barrier before they're allowed to continue forward. And the typical way of using is that you want to guarantee that certain computations have been finished before you move to the next step. And this is the end of the second lecture. And what remains now is that you saw that I have a couple of hands-ons there. So I will be here at least maybe 10 to 20 minutes to see if anyone has any questions. But the actual lectures for today end now. And I thank you for your attention. And I hope that you will join me again tomorrow morning when I start talking about OpenMP tasks.